If the latest images from the James Webb Space Telescope impressed you, what comes next may completely change the way you think about the universe. A new observatory is looking at the cosmos in a very different way. Instead of focusing primarily on individual galaxies, stars, or nebulae, the Euclid Space Telescope is designed to investigate the enormous structure connecting them all. Launched by the European Space Agency, Euclid was placed near the Sun-Earth L2 point, roughly 1.5 million kilometers from Earth. Its mission is ambitious: create a huge three-dimensional map of the universe and investigate how cosmic structures have changed over billions of years. But Euclid is studying something we cannot directly see: dark matter. Scientists know dark matter exists because of its gravitational influence. It helps galaxies remain bound together, affects the motion of galaxy clusters, and bends the path of light traveling through space. Euclid can exploit that last effect. As light from distant galaxies travels toward Earth, gravity from matter along its journey slightly distorts the apparent shapes of those galaxies. This phenomenon is called gravitational lensing. The distortion can be incredibly subtle. A single galaxy may reveal almost nothing. But when scientists measure the shapes of enormous numbers of galaxies, those tiny distortions become statistically meaningful. Together, they can reveal the invisible distribution of mass across the universe. That is what makes Euclid so important. It is not simply photographing the universe. It is attempting to map the gravitational framework beneath what we can see. The first major observations already demonstrated the power of this approach. Vast numbers of galaxies appeared across enormous fields of view, revealing clusters, groups, filaments, and other structures spread across cosmic distances. At first glance, the universe can look like an enormous collection of unrelated points of light. But those points are not randomly distributed. Galaxies tend to gather along immense structures called the cosmic web. Between these structures are enormous regions known as cosmic voids, where galaxies are much less common. The scale is difficult to imagine. Filaments can stretch across hundreds of millions of light years, while massive clusters occupy regions where huge concentrations of matter have gathered under gravity. And the visible galaxies may only represent the illuminated portion of something much larger. Dark matter appears to provide much of the gravitational scaffolding. Galaxies form within dark matter halos. Groups and clusters develop where those halos become concentrated. Over enormous periods of time, gravity pulls matter into increasingly complex structures. The result is a universe that resembles a gigantic network. But there is another mystery hidden inside that network: dark energy. Scientists observe that the expansion of the universe is accelerating. Something appears to be driving this accelerated expansion, and that unknown component is called dark energy. Dark matter and dark energy therefore appear to influence the universe in very different ways. Dark matter helps structure matter through gravity. Dark energy is associated with the accelerated expansion of space. Euclid is designed to investigate both. By measuring galaxy shapes, positions, distances, and the distribution of large-scale structures, scientists can reconstruct how the universe has evolved. The goal is not to find one strange galaxy. It is to study enormous populations of galaxies and search for patterns. And that is where Euclid becomes truly powerful. Its observations can turn the universe into a massive statistical experiment. If the structures we observe match predictions, confidence in current cosmological models becomes stronger. But if consistent differences appear across huge samples, scientists may have to reconsider assumptions about dark matter, dark energy, gravity, or the evolution of cosmic structure. The most important discoveries may therefore not come from a single spectacular image. They may emerge from millions of tiny measurements that, when combined, reveals something about the universe that no individual observation could show. And Euclid is only beginning that investigation. The deeper Euclid looks into the universe, the more complicated the cosmic picture becomes. One of the most important clues comes from the enormous regions between galaxies. These cosmic voids can stretch across hundreds of millions of light-years. They may contain relatively few galaxies, but that does not make them scientifically empty. Their boundaries, shapes, sizes, and evolution are influenced by the distribution of matter surrounding them. As gravity pulls matter toward denser regions, voids can become increasingly empty. That process leaves behind information about how the universe has evolved. In other words, even apparent emptiness can contain a record of cosmic history. And Euclid has another advantage. It is effectively a time machine. When the telescope observes a galaxy billions of light-years away, it is seeing that galaxy as it existed billions of years ago. The farther away the galaxy is, the further back in cosmic history we are looking. By studying galaxies at different distances, scientists can construct a kind of timeline showing how the cosmic web developed. The early universe began with tiny variations in density. Some regions contained slightly more matter than others. Gravity amplified those differences. Dark matter gathered into increasingly dense structures, and ordinary matter followed those gravitational wells. Eventually, stars formed. Galaxies emerged. Groups and clusters developed. And over billions of years, the enormous cosmic web took shape. But exactly how quickly this happened is one of the major questions in modern cosmology. If Euclid discovers that structures developed exactly as predicted, existing models become stronger. But if repeated measurements reveal systematic differences, scientists will have to investigate why. Perhaps our understanding of dark matter is incomplete. Perhaps dark energy changes over time. Perhaps gravity behaves differently on enormous scales. Or perhaps some assumptions about the early universe need to be revised. One unusual observation would not be enough to rewrite cosmology. Science requires something much stronger. The pattern must appear repeatedly. Independent measurements must support it. Alternative explanations must be tested. And the results must survive attempts to disprove them. That is why Euclid's enormous survey is so valuable. It is designed to search for statistical patterns across vast numbers of galaxies rather than relying on isolated discoveries. The amount of information is enormous. Researchers cannot manually inspect every galaxy. Advanced computational systems and machine learning techniques are increasingly important for classifying galaxies, measuring their shapes, identifying structures, and searching for extremely subtle correlations. This represents a new era of astronomy. Human beings are no longer simply looking through telescopes and interpreting individual objects. We are using machines to analyze patterns across enormous portions of the observable universe. But there is an important limitation. Measuring something does not necessarily mean understanding it. Scientists can measure gravitational lensing. They can estimate where invisible mass is located. They can track how galaxies are distributed. They can measure the expansion of the universe. Yet the fundamental nature of dark matter remains unknown. Dark energy is still mysterious. And scientists still debate whether our current description of gravity is complete on the largest scales. That is why Euclid's mission could become so important. The telescope is not expected to suddenly discover an alien civilization or uncover a hidden cosmic machine. Its potential impact is much deeper. It could test the foundations of our understanding of the universe. If its measurements agree with current models, we gain stronger evidence that our picture of cosmic evolution is broadly correct. But if precise observations repeatedly reveal contradictions, Those contradictions could become the starting point for new physics. The universe may not be hiding one spectacular secret. It may be hiding thousands of tiny discrepancies. And Euclid was built to find them. The ultimate goal is to understand how the visible universe emerged from an invisible framework of matter, gravity, expansion, and time. James Webb is allowing us to examine individual galaxies and ancient cosmic environments in extraordinary detail. Euclid approaches the problem differently. It is trying to understand the universe as a whole. And as its enormous survey continues, the most important discovery may not be what the telescope sees. It may be what the data tells us about everything we still cannot see.